Hi, I'm Sigrid. This here is little Tux who's helping me doing these videos, and today we're going to talk about iris. Well, perhaps not so much about iris per se, but we're going to create on iris a simple, straightforward Bayesian regression model, fit that with Hamiltonian Monte Carlo, and all that using TensorFlow Probability, or rather the R wrapper to TensorFlow Probability, Tf Probability. Here's its web page with the documentation and articles. But to make this concrete, we're just gonna jump to RStudio and get started. So here we have RStudio open, and I assume you don't have TensorFlow Probability installed. So we're gonna start with this. Now if you do TensorFlow install TensorFlow, this will also give you TensorFlow Probability. As you see, I haven't entered any arguments, which means I get the current stable version, which is 1.14. So 1.14 is the TensorFlow version, and the TensorFlow Probability version will be 0.7. Now this was already it. Pretty quick install. Let's see if everything went as it should, and load TensorFlow. There we go. Just check the version. Everything's okay. Okay, so we have 1.14. We also want TensorFlow Probability, right? Tf Probability, the R wrapper. Oops. This was one parent too much. This one tool not enough. Here. What's going on here? There we go. Okay. Bit of a cumbersome start, right? So let's load the tidyverse for some little data manipulation we're going to do, and that's it already. Now, one thing about TensorFlow, as of 1.14, we're still using graph execution by default, which is not so nice for this video, because it's easier when you can really inspect the tensors, what's inside them, see the values. So we want to use eager execution. One way to get this, as of today, is like this. We say enable v2 behavior. And now one thing this gives us is eager execution. And now we are set up. Well, apart from the data, so we want to use iris, right? Everyone probably knows iris, but we want to pose the problem as simple as possible for this intro. So there we have 3 classes. We just want 2 classes. So this means I'm going to construct a data frame and filter out one of these. Let's say I don't want the setosas. There we go. But one thing still is I want this column to be numeric to work with. Actually, what I really want is I just want zeros and ones, which makes it easiest. So let's do that. Oops. This makes it numeric, and then let's just say we do -2. So that should give us zeros and ones. Let's see if that's true. Oops, not iris, but of course the DF, the new data frame. So this has ones and zeros. Okay, that's what we want. So we have a 2-class problem, which one way to fit is logistic regression. Now we're gonna use TensorFlow distributions for this, or to be precise, we're gonna use the Tft joint distribution sequential, which is a function that allows us to model joint probabilities. And what we're gonna have is we're gonna have priors for the coefficients for our 4 predictors, right? We have 4 predictors, each one's gonna have a coefficient, and we're gonna say each coefficient a priori is gonna be normally distributed with a mean 0 and standard deviation 1, which is a bit strict perhaps, but yeah, let's see how it works. And then, so we have our predictors, and for the class problem, we're going to use a binomial distribution. How that? Yeah, because if we have just 2 classes, the binomial reduces to a Bernoulli, and we can nicely work with the binomial in TensorFlow probability. So let's define this. This TFD joint distribution sequential takes a list of distributions, and each of these distributions is going to be normal 0, 1. Should be a comma there, so it means 0, standard deviation 1. Now what I can do is, I have 4 of these, I can just copy paste them. There we go. These will be our 4, let's say, betas, beta 1, beta 2, and so on. And now we're going to have the binomial, which takes in these coefficients. And to express this dependency, we will have a function with an anonymous function with parameters, or let's say b is shorter than beta, b4, b3, b2, b1, and the binomial, this is just TFD binomial. Now you see we have this parameter total count. This should be 1, just a single draw. Let me just put this here on another line. And now we can, a nice thing is we could either specify the probabilities here or the logit. And logit is the log odds, which otherwise we would have to construct ourselves. So if you just say logits, we're basically all good, nothing else to do. And how should our logits look? Well, we need to combine those predictors using the coefficients. So this will be, let's say, b1 times sepal length plus, or I'm going to put them in one line. Let's make this a bit longer here. Plus b2 times width plus b3, let's check, times the length plus b4 times the width. That should be it. Let's just make it a bit bigger here. So that's our logits, binomial, everything should check out so far. So all this, of course, should be our model definition. Let's see if this works. Okay. Now TensorFlow is awake, as we can see. So 2 things we should always check after we've defined a model are the following. We should see, can we generate samples from this model? A single sample. Does this work? And how do these samples look? Well, okay, So here we have our 4 coefficients. This looks pretty good, and here are the sampled class memberships. Okay, all ones, but I mean this is for before training, so this looks good. The second check is, can we use the model now to determine the log probability of these samples? So, like this. Oops. Okay, so we got 100 values here. So which means we got 1 log probability for every item in the dataset. And this is not what we want. So we want a global log probability for the complete dataset. What can we do? Well, there is some transformation, technically also distribution, which is called independent distribution. So this would be TFD independent. And if we check this, it has a reinterpreted batch endims parameter, which we can pass to move dimensions from the batch dimensions, which we have too much of at the moment, to the event dimension, which we don't have enough of. So with that, we should get the correct shape. Let's check. Let's put this in here. There would be an additional TFD independent. And here was our binomial. Now we need the reinterpreted batch endims equals 1. So all this stuff, which was a batch of 100, should now be 1 event of event size 100, of dimensionality 100. So here we go. What does it not like? We probably have a parent missing, right? Okay, there we go. Then we should also move this a bit here. So this should be better now. Let's see the samples. They should still look like before. Well, all zeros this time, for whatever reason. And now take the log prop, and yeah, so this is what we want. We have just 1 value here. Okay, so far, are we good? Well, when we do the Markov chain sampling, we need to work with batches. This means we need to be able to do something like this. This would mean we have 2 chains, which chains always end up in the batch dimension. So what we know from normal TensorFlow is the batch dimension, 0 or 1, if we count 1 based. So let's see, can we just have can we have these 2 chains? Oops. Evidently we cannot. We get some incompatible shapes error. Okay. There is one other thing we need to do. And this is, so as we now work with batches, we need to expand these parameter samples to be 2D. In Python, this would be such a none you would add to get this expansion. In R, we can just do a null instead. We could alternatively use tf$expand dims, but this here is perhaps a bit shorter, so why don't we stay with this? I need this to do this for every of these parameters now. This one too. Oops. Perhaps just do it like this. So we have a bit more, it's a bit better to read. And this one we still need as well. Okay, so here we go. Now let's check, does this do it? At least the syntax was correct, which is already good. And now let's say if we can sample. Okay, now how do these samples look? Scrolling up, we see for every parameter we have 2 samples now. This is nice. Now we should make sure we still get scalar log probability for this model. Indeed we do. So we had a batch of 2 and we have 2 log probabilities. So yeah, this actually looks great. We can work with that. Now if you don't like this copy pasting here, I mean, now we had 4 coefficients, we could have 40. Can we do this a bit nicer? Well, we can work with matrices instead. So let's say we had our DF, let's say we have a model data, which is just our predictors. So this would be all but the very last column, right? Minus species. And also we want to have this as a matrix. Let's check this model data. Yeah. Okay, so we have our data as a matrix. Now we need the parameters as a matrix too. And what we can do to just have independent distributions, we can use something called Tft Sample Distribution. We pass in a distribution like Tfd normal, 0, 1, just like before. And it also wants a sample shape. In our case, this will be 4. Can we do this? Okay, yeah, we see this has an event shape of 4 now, which is what we want. Let's try a bit what kind of shape stuff we need to do here. So let's call this just d underscore and take some samples from this distribution. Let's say I have an s underscore, which is d underscore pipe tfd sample. And let's say, let's take we're gonna work with 4 chains anyway, so let's take 4. How do these samples look now? 4 by 4. Okay. Now actually I think it's easier if we just have different numbers everywhere. So let's say, just for example's sake, we have 2 by 4. Okay, I'm just gonna write this down so we don't forget it. Okay. Now these are our parameter samples. We know our model data. Actually, let's just perhaps see again what are the dimensions of model data. This is 100 times 4. Okay. Now, how do we want this to end up? We want the output at the end. Let's also write this down perhaps. We are working with a batch dimension of 2 and we have 100 items, so an event size of 100, so we want this at the end, which means, what do we need to do when we now multiply this $tf$mapmal? Well, these 4s here need to match, and I need to start with this here. This is clear, so I take this first, then I take my model data. Here we go, and the model data I still need to transpose, and I think this is called transpose B. And let's just check what happens if I execute this. okay, I think we need to go to TensorFlow and check for the matmul. Go to the API. No, it's loading a bit slowly. It's loading pretty much slowly, probably because I'm recording the video right now. Okay, there we go. Actually, I should quickly switch to the Firefox so everyone can see what I'm doing. I want to search for the matmul. So transpose B actually was correct. What did we not do right? Is everything okay? Just let me check the, yeah. This was $, model data, transpose B, we did not pass anything. Okay. Okay, now we still got another error. This time it's because we don't have the same data types here. We can quickly fix that and cast the model data to whatever data type the betas have. So S underscore $D type. And now we should have this working. Let's see. Okay, so we get something out of shape 2,100. There we go. Let's just take this line here and copy it in here. So the total count of course stays, but we need to replace the logit stuff. Here we are. The S we should replace with model data. Okay. No, not with the model data, of course, but with the parameters. So actually I'm doing it a bit backwards. We're going to rename those to betas. We have then here betas, $D type, and this here we don't specify them one by one anymore. This will just be betas. And of course we also need to paste this here. Here. So there we go. Now we've just this one line here, and we've replaced all these individual adding up by one matrix multiply. Let's see if I got this syntax correct. Looks like so far. And we still have a scalar log problem. So now it seems like we really finished setting up the model. So don't panic. We went through this just to point out what to pay attention to. But now it's going to be smoother from here on. So we're now ready to define the optimization target. Gonna call it logprob, and it will be a function of the coefficients, so our betas, and it will be the likelihood under the model of the data and the parameters. So we have TFD log prob. And so now we first have our betas, our coefficients, and also our target, which we haven't, we should isolate that so it's easier to deal with. Let's say our target. Now we had this df. Now we only want the species, right? Species. And we want this in matrix form. There we go. Now we can use this here. Now when you work with this matrix formulation of the joint probability distribution, we need to transpose the target as well. So, and we will need to cast the data type. So we have the same data type in the coefficients and in the data. So let's have a tf $cast target beta star d type. So that should in principle be it. Let's see. Okay, there we go. So that's our optimization target. Now the HMC algorithm is gonna need some initial values to start from. And what works fine in this case, not in all other cases, is we just can take some random samples before training. So let's say we define our initial betas. We just sample from our model. And now one important thing here is how many samples are we going to get for the initial values. This will define how many chains HMC will work with. So let's just isolate this up front. And chains, we're going to use 4 chains here. And then we're going to have n chains samples. Now let's say I did this. Should probably define it first. Again, if I did this, I don't only get the coefficient samples, parameter samples, but also the sampled classes, which I don't want. So we're just gonna take the first part here. There we go. Now these are our initial samples. Now for the sampling itself, so we're gonna have a Hamiltonian Monte Carlo kernel for that. Mcmc Hamiltonian Monte Carlo. Let's see from the parameter list what it needs. It's gonna need the target log prob function, a step size, and the number of leapfrog steps. So let's start with the target log prob function. We already defined this one. This is the log prob without the parents. And step size, one thing that often works well for a start is 0.1, and we can choose a number of leapfrog steps of 20 here. So in for other data sets, always makes sense to experiment with those two. Also, you could have different step sizes for the different parameters. This may also make sense to vary. So here this is our Hamiltonian kernel, but we can go one step further and have some adaptive step size adaptation during the burn-in phase. So we just have this simple step size adaptation. This will gonna need this inner kernel we already have, the Hamiltonian Monte Carlo kernel, and the num adaptation steps. We can also change some other parameters, but we're just going to leave them how they are for now. So let's add this. And so the number of adaptation steps we want to change. Here again, we just extract that variable here. Let's call it n burn-in, number of burn-in steps. Let's say this should be 1000. And we're going to use that here and also in some later place, n burn-in. So there we go. There's our kernel. I guess I should, in this case too, just define this first. And here we are. Okay, fine. We can actually go sampling now. For the sampling, there's a function Mcmc sample chain here. We're just going to take the kernel and the number of results. This will be the number of steps we want to sample for after the burn-in phase, and it needs a current state, which will be our initial values. So if we now we're gonna now put all this in a function. Let's just call this sample. We take our HMC kernel and so now what we need to pass, apart from the kernel itself, are the num results. And here let's just extract that too, call it n steps. Let's also say this should be 1000. So num results will be n steps. And also we need the current state. This will be our initial betas here. So this is our sampling function. And now there's one thing. Why did we put it in a function? Well, in general, we're using eager execution to be able to nicely inspect the values, and it's just so much nicer to work with overall. But the sampling really should run on graph for performance reasons. So I'm gonna say sample is tf function sample. So this is gonna run on graph. And now we just can execute this. And that should be fine. Well, it is not fine. We're missing something. Okay, we have not defined these n steps. Doing all this again. And now you see we're actually doing the sampling. And this was quick, so it's already finished. So we have our res. So what is this res now? Well, we have a tensor. Let's see, just one tensor of shape 1000 times 4 times 4. So what is this? 1000 is the number of steps we're using in sampling, 4 is the number of chains, and the other 4 are our 4 parameters. So now to do some analysis, we're gonna bring this in a form we can work with nicer. But let's just take this raw form to obtain two diagnostic measures. So one measure would be the effective sample size. So the chains are gonna have some autocorrelation, and this is gonna tell us how many independent samples we would have, so to say. And we can obtain this. There we go. And let's also save this away for later. So there we are. Now the other measure would be the R hat, or as it's called here, the Mcmc potential scale reduction, so which is a measure of how well the chains mix. Extracting that. Also gonna call it potential scale reduction. There it is. Let's already take a quick look. And we see it's all four, so we have the 4 values for the 4 parameters, and it's all pretty close to 1, which is exactly what we want to see. Okay, now that we have our sampling results, I'm not going to type in all the visualization and extraction code. So we will just follow along through this code and see. So first, we're going to take a look at how well did the chains mix, or how big is autocorrelation. The res is the tensor, right? But from now on here, with these samples, we're going to work with R objects. So we have a list here, one item each for the parameters, with the 1000 samples and 4 chains. So, and some prep code, some plotting function, and now we can plot the samples. So how does it look? Okay, we see at the beginning it still is this does not mix so well, but after that pretty well. Actually, this is the thing when you do things live, right? So I did not have this behavior before, but there's always some randomness in there, and so this can happen. If consistently there were problems, you would vary the step sizes, the number of leapfrog steps, or even possibly the sampling period. But in general, this works really very well. So then, of course, we want to have a summary of our parameters. We want the posterior means, standard deviations, also the highest posterior density intervals, and we're gonna get all this now. So this part extracts the posterior means, standard deviations, highest posterior density intervals, and we're gonna put all this in a table together with the effective sample size and the potential scale reduction, which we already had above. Let's do this. So, and let's see how this looks. Okay, there we are. Here we have the means and deviations, upper, lower, effective sample size, and the R hat. So the effective sample size would be nice if that would be a bit higher, but the R hat is pretty nice. So, of course, we are also interested in how well can we use this for classification, right? And to keep this video from growing to infinite length, we're gonna do a quick and dirty prediction just using the actually not the map, but the posterior mean, which we can do in a quick way. So we have our model data, we have the posterior mean here, and these we can just matrix multiply, right? So this will give us the combination of the coefficients of the data using the coefficients. And now this was used as the log odds for the binomial. So we need to undo the log odds, which is done using the logit or the sigmoid. And here again, we're just being lazy. I mean, it's quick, easy to write this function, but TensorFlow has it, so why not use tf.sigmoid? and we need to have this numeric again. So let's get our predictions. And we're gonna make a cutoff at 0.5, so we have the classes 1 or 0, which we were working with. Here we go. And now let's just see how well do these match visually, adding them to the data frame. And here we go. So let's go up. Let's just look at these two columns here. So this is the real 0. Don't know which type of flower it was actually, but one of the two classes. And all these predictions are correct. Here's actually one which is not correct. Here also not correct. Then correct again. Two others. So one of these class, we have 4 from one class which are predicted. And now for the other class, these are all correct. So perhaps even with a different cutoff we would get a better result, but these are pretty reasonable results. So that's it for this video. For some more background on this, we can, I suggest you could look at the TensorFlow for R blog, where we have blog posts not just on deep learning, but also on TensorFlow probability. Here in this category, probability and statistics, is all there is at the as of today using TensorFlow probability. And there are, as of today, 3 posts using the joint distribution sequential for modeling. But of course you're also welcome to look at the other posts, as well as posts in general from this category. So yeah, that's basically it for today. So thanks for listening, also from Little Tax, and see you another time.